So good morning, everyone. We will start. Happy Monday. Welcome to class. We are going to finish a topic we started last week on Friday, and we will start a new topic. And we are the first day in the new month of November. And so happy Monday and happy new month. And this happens to be also the 11th week in the semester. And the inspiration for today's picture on the right is a game I know involves 11 players. And so when I saw the number 11, I thought of soccer. I remember in one of the warm-up questions we have had, I think a couple weeks ago, or when we first talked about logistic regression. There is the logistic regression idea there has to do with odes, and horse race was something that came to mind, and that was a reason for making up a warm-up question for that day. And because we're in week 11, and we're going to use this metaphor for this game in a couple of different ways. I want to form today's warm-up question around the game of soccer. I know some of you are big fans of soccer, others are not. Some of you play, others don't. But today's warm-up question is for everybody, and it has to do with telling me your all-time favorite soccer player, man or woman, big World Cup or smaller tournaments around, or it could, whatever it might be. But let me know who your favorite, all-time favorite soccer player is. And Alexander is going to be the person who is going to type up the warm-up question for the day. So people are already typing up, but Alexander, when you get the chance, Alexander Mesic is what I'm thinking. He sounds like, the name sounds like a soccer player. I'm not sure if he plays soccer, but go ahead and type up the question. What is your all-time favorite soccer player? And all options are open. You just tell me, let me know that. Speaking of soccer and game, we will have a two halves situation today. The first half will be actually used to finish up this topic, and the second half will be used for looking at our code. You had a busy weekend. I know you had to submit your assignments, and most of you have done a good job on that one. And so we are going to kind of go back and finish off the discussion we started with trees, and we had so very many good discussions around it, why they are needed, and we looked at them both for the time when they're used for solving regression problems and when they're used for solving classification problem. And I had a good list of advantages. And the biggest of all was that they are trees, that is, decision trees, are interpretable. And so there is the appeal. The model itself is a tree, and we can show it to somebody else, and it's easy to interpret. And it could be sometimes mapped to our way of processing things when we make decisions. The disadvantage was that they are not trees, that is, a decision tree is poorer compared to other supervised learning methods when it comes to their prediction accuracy. What do we do then? Well, we say we'll use a bunch of them. We'll get to use many trees, and that is in a nutshell what we will be doing today. So we'll use a bunch of trees. That soccer picture right there, in addition to showing a goal that looks like a very nice one, there is also some trees behind it. So we haven't forgotten what we are up to doing. And so I'm going to be talking about this one, and I'm going to go fairly fast so that we get to see the implementation aspects of the R code implementations of the aspects of this. Okay, before I get started, does anybody has got any questions or anything to me? And this is the place where you would unmute yourself and ask if there is a burning question before we get to start looking at the topic for the day. Because people are typing up their favorite soccer player of all times. Anybody has got any question for me? A quick one? Okay, you're all ready to start. when we talked about cross-validation, which was the topic we had right before we started talking about decision trees, I emphasized and I repeatedly told you how important it is that you all have a good understanding of what cross-validation means. And that was used in the context of having to evaluate how a method is done. So you've got this k-fold, you've got the cross, and the validation part was both important. And so that was how we would assess. We learned how to do them right, and we learn how to avoid having to do them wrong. And cross-validation will be the method of choice for having to talk about how well a method is doing to validate it. But we also used it to find out trees, and especially the pruning aspect of it. And so that was the reason why the order was in that fashion. So we came back to classification methods or tree-based methods after we looked at cross-validation. And at that time, I told you there is one thing that I will just mention it for 1 minute. And here is the 1 minute version of it. So cross-validation is about having to find out how good a method is, to talk about its prediction error in a way that would split your data first to training and test set. And so you are leaving out something, and then you are dividing this into folds and using you play a game in a way. And so you you train on the remainder of the one that you have left out, and then the roles get changed. And so all of this was to find your prediction error around an entire method. A close relative of that one is when you, in a statistically rigorous way, you want to find how a parameter in a given model, in a fitted model, how a parameter would do in terms of the standard error it has. And if you were to do that, and you still remember, cross-validation is about this ingenuity of it was we don't have, the universe is not giving us training data all the time, and so we're reusing it. That's why it came about. And if we are going to talk about having to find the standard error around a parameter, and we still have this one training set to do, what would you do? There is a technique called Bootstrap, and Bootstrap is just like you would know it. You are going to solve this problem by your own Bootstrap. That is what you have, and you still are going to find what standard error you could associate with parameters in a model. The Bootstrap method would be used. What does it do? Well, what it does is you are going to sample with replacement. So Bootstrap could simply be called as sampling with replacement. So I did not have time to devote an entire lecture to it, but if you just remember, Bootstrap means sampling with replacement, you're fine. So the idea then will be similar to what happens in cross-validation. It is about having to use a portion that you have left out to calculate certain things, but that is used for typically it's used for finding standard errors around parameters of a model. Now, let me assume now that I've told you, you know Bootstrap. Bagging is a way to work with multiple trees where we are going to be doing something that is going to begin to address the problem of trees being poorer in their prediction accuracy. And because they are not very good in getting high prediction accuracy, we're going to use many of them. And by many of them now, we are going to mean to use to bag them. So we are going to have trees that are going to be grown from the same training set. We don't have plenty of them. We're going to use, but instead of having to deal with trees, having their variance and so on, pruning them, we're going to grow a number of trees, very many, in fact. And this time we're going to have to bootstrap. We're going to take from the same sample with replacement, a number of them, and then we're going to grow trees and try to get the best out of them by averaging them. And by averaging them, we will hope that the value that we would get would be a good prediction. Anything that is about variance will be kind of left out, will be smoothed out because of the averaging. So you get a chance to make a lot of mistakes, so you repeatedly do them, but then by averaging, then you get a better sample. That is what bootstrap aggregation means. Another word for it is bagging. So the idea behind bagging is to use repeated trees from the same training set that we have to grow many trees, and then average them out to do our predictions. And if the reason that this would hope to do well is because if we have n independent observations, and let's call them z1, z2 up to zn, and each one has got a variance sigma squared, the variance of the mean of these would be sigma squared divided by n, and therefore it has been reduced. So if they were independent, and now by having to grow trees from the same training set and repeatedly them with replacement, we're sampling with replacement, which is what Bootstrap aggregation is. The hope is to get to reduce the variance. This method is called bugging. And it sounds like you have not probably gained a lot of things, but when these things were introduced in the 90s, it was a great idea. Trees, we learned last time to grow them all the way down to get, reduce their variance, and then by the time, if we were to really grow a bushy tree, then we may overfit. And to avoid that, we learned how to go back and prune the tree. This time now, when we are bugging, we don't need to do that because the pruning is not needed because we have many of them. So by growing very many trees and by taking an average, we will hope to reduce the variance, and that is called bugging. This is the math description of it. So instead, what we will do now will be to have B, capital B, different Bootstrap training data sets. Bootstraps means you are taking the sample with replacement and growing these trees and taking the average, basically. And just the same way we did last time when we were talking about decision trees. For the discussion we will have today about bugging and the other things that would come, we've got two of them, if you have noticed the title. We will work both with regression and classification because it's easier to talk about in terms of prediction. Regression, we first introduce it in terms of regression, and then we'll say, here is what we will do if the problem was classification. So in this case, because it is regression, we take an average. And so we had B of them, we add them up and we divide it by however many we had, and that will be our estimate. Just like we had a tree and we went around and divided, blocked them up, and so the terminal nodes were the ones that we would use to predict for each observation. Now we are using the entire tree for the prediction, and by having to average them, then we would smooth out these variances, and that is called bugging. If this was when it was regression. If it is classification, then what we would have now is we've got a bunch of them, very many trees. By the way, this, when I say many, I'm talking like 100, 200, 300, 400, 500 trees that you would grow. You're not pruning because you are averaging them. So when it was regression, we added them up and took the average. And divided them by how many trees we have. And so that was an average. If it is a classification and we have many trees, then now we will count how many times they have voted. And so we will say, if it was, for example, a binary classification, class 1, class 2, we'll say how many of the trees voted for class 1. And if the majority voted, then instead of averaging them now, we'll say we'll go with the majority. Similarly, if we have multi-class, we divide them up in the right way to determine what majority means, if it's more than 2. Just simply stated, when it is regression, we take average. When it is classification, we take majority vote. Otherwise, the idea is that. So what is bugging? Bugging is using many trees and taking an average or majority to avoid variance. Here is an example of how this works for the heart data set we saw. That was the last example we saw last time, and there was 13 or so predictors that were used, and people were complaining about chain pain. They have the chain, and so do they have heart disease or not, is the classification. And here is a few plots that you would see. One of the plots you would see is what happens when you just a single tree, the way we learned last time. And that is shown with a broken dotted line. What you see here is on the horizontal axis is how many trees you're growing, and on the vertical axis is error. In this case, because it's a classification, whether the person has been correctly classified with heart disease or not is what you see. And so the error is how much mistake you have made. So when you use one tree is what you see, the broken lines, that's the error you get, 0.25. And these other 4 things are different things. And one of the things that I want to show you is what the bugging does for it. When you do 50 of them, when you see hundreds of them, when you see 150 of them, when you see 300 of them. And so there is a little bit of up and down, but it at least has reduced compared to the single tree one. The other two, the golden one especially, will be the subject of our next discussion, and that's what random forest is. So it is getting some improvement. The lower two curves, I will come back to them because they are going to talk about an error associated with just the method I just told you now about bugging. Okay. In fact, that's probably a good place to start. This is the details of this figure. Random forest was something that improved over the bugging that I just told you, but the other two curves were errors that I didn't have it. I didn't explain. So let me hold off to the random forest discussion for a second and tell you what these other curves were below it. And these are called out of bug error. For a second, go back in your mind to what we did in cross-validation a couple lectures ago. We said we are going to have to hold out a portion of the data set for testing, and we're going to train on the remainder of it. And now the other guy changed its role, and now this will become the new place where we will do for testing, and the remainder, everything else now will be used for training. And so we keep on doing this, and that's what folders were. And if we were to go take this all the way, we would come to a place where we would have in each one of these folds just a single element. And that's called leave out one cross validation. We called it that way. And we said, no, that's not a good idea. Why? Because it could not shake up the data very well. And also potentially, if I'm just taking one out and I'm looking at the rest of it, there will be a lot of computation. But then we said, oh, no, we don't have to worry about the computation part because we get that for free. And I should have showed you something that looks like a math expression that gets us that. And then that had to do with leverage and things like that. That same idea could be extended to talk about these bugs now, the things that you have done by bootstrapped samples and the trees were grown. And the math that works in favor for us now is that if you talk about these bugs now that are made, you could find that, you could show that every time something is tested on one of the bugs and the others are used for the other ones, there is a relationship between how many of the trees could end up in 1/3 and 2/3 of them. And so an out of bug error is something that you could find out by seeing what the contribution of a predictor would have been if it was not selected in the tree that is grown from the bootstrap. And so if you were to look at that and then find out what the error would be associated with it, that's called an out of bug error, OOB. And so this, because of how the bootstrap is done, because of the replacement, there is a 1/3, 2/3 relationship, just like the leave out one cross validation had a relationship with the hat function that I told you about leverage. You can calculate errors this way. And that's what you see in this figure, that you see for the green and the blue curves. So that is an out of bug error for something about bugging, which is compared to what the bugging was showing you was lower, and an out of bug error that is associated with random forest, which is even lower. And so now that I have told you what these out of bug errors are, these are things that you can calculate if you have a software, which we'll see in the second half of our soccer game today. Then we see that there is an improvement that it has given. But compared to bugging, random forest gave an improvement. And let's stop for a second worrying about the out of bug errors and just try to see where random forest is coming compared to bugging. Bugging was doing many trees. These many trees were done exact same size with replacement, and I'm growing from the same sample. I grow a tree, and I didn't worry about pruning. I grew it all the way to the end, a bushy tree, and then I grew another bushy tree, another bushy tree, hundreds of them, 200s of them, 300s of them. And so they were all equal, and everybody was treated equally. Every predictor was seen the same way. And so these trees were at the end added up and averaged, or majority vote was done when it was classification. The same person, Bredman is I think his name, who came up with the bugging idea in the 90s, a few years later came up with this idea called random forest that would improve what buggings would do. And the idea seems a little bit crazy to begin with. And the idea is this: If you were adding these trees and then averaging them, or if they were classification, you were taking the majority, it would help if the trees were actually uncorrelated. Because now I would get something that this tree is telling me that the previous tree didn't tell me. And so the way he came up with this one to decorrelate these trees was bizarre. He thought, and this is the place I have repeatedly told you where randomness comes to your rescue. Instead of taking now, I had a training sample and I bootstrapped. The only difference I have made between this bootstrap and the other bootstrap was that I did with replacement, it was exactly the same size. Instead of doing these trees the same way, I'm going to select among the predictors I have got M of them, or P of them. P of them is what actually is the right one. I'm going to select each time when I build my decision tree, instead of treating every predictor, I'm going to have a select few of them and leave out the others. And the ones that I would select are going to be chosen randomly. So instead of have every predictor participate in the decision-making process when you were building the tree, and we were using them, you remember how it was, they, did this one help me make the most of the, going when I go left and right, did it help me make progress? That was what we see, but everybody was a candidate. Instead of having all of them, now in each decision time, in a decision place in the decision tree, there will be a selection of the predictor that will be used, and that will be done randomly. So the number will be drastically reduced. In fact, a number that would work well is if you take square root of P. So if P was 100, you take square root of 10. So out of 100 possible predictors that are all candidates, you randomly pick only 10 of them to make a decision on one of the branching points. On another one, now you do another random selection, and on another random selection, and so on. So the idea then now is, because you have left out many, you may feel like you're losing, which you probably are, but you have made the trees uncorrelated, and therefore, and then the chance that then somebody else would show up, one of these predictors would show up in some of these trees later on, is high because they are randomly selected, and we've got many of them. By having to have many of these trees, but this decision point is being reduced, how many predictors you are using, but choosing them randomly, you decorrelate. And that turned out to be a very, very, very clever idea. In fact, I have told you last time, you need to know about how random forests work. You will not implement them yourselves, because whether you're using R or Python, there will be a package that will do this. Is what happens in them. So there is a reduction in how many of the predictors are considered in the decision point. That is done in a random fashion, and the number is chosen to be drastic, order of square root of P usually. So that's the difference between bugging and random forest. Here you have reduced how many predictors are considered for making decisions in each decision point in the decision tree, and that number is typically square root of R. So if I go back now to the same example I showed you earlier, this is what you see. So the bugging was the black, and random forest with the color. The other out-of-bug errors correspondingly show what advantage you have gotten, or what the calculations that have came. But as a method, what we are comparing is just the bugging and random forest is doing better. And this is not just for this data set. It is actually true, and it is probably, you will be surprised how many times, including my own research, where random forest does a very surprisingly good job, and you probably don't need to do much more than that compared to many other more sophisticated ones. And so let me show you a couple examples. The first example I will show you is genomics data. This is some 350 or 349 patients, and so this is about gene expression, and they are going to be classified in one of 15 different cancers. One of them is normal, and the other 14 are different types of clusters. And what is used to do these predictions is 4,780 of genes measured, and so there is a lot of gene expressions that are used to determine for these patients. And this is a very good example of what it means to have high dimensional data. So there's lots of things. There are lots of predictors. And there are about 20,000 genes in humans, is what the second bullet is trying to tell you. So before we get to see how random forest does on this one, let's first see what people typically do when they have such a huge number of predictors. What they do is screen. So you have 4,700 genes, and out of these, 500 of them are selected by looking at their variants. This is called, I have to spend half a minute telling you about this one. Last time when we talked about cross-validation, I told you about how to avoid to use it in the wrong way. And the wrong way was when you do screening of this kind, you have to carry on your cross-validation also to the second step, was what I told you. Now I am kind of headed the same way, but this time I want to point out that what you're doing in terms of screening is unsupervised. So you looked at 4,700 genes as predictors, and out of them you selected 500, but not by looking at the labels, not whether they, in your training, whether they were one of these 14 different um, uh, cancer types or healthy. You're not using that. Be just looking at the variants, and it is usually true that the ones with the largest variants in the training set have got the largest chance for them to be good predictors, and so you chose them without supervision. And so I have 500. So the 4,700 is now reduced to 500. And now we're going to use random forest to see how this one would do. And here you have, on the horizontal axis, you've got the trees, how many trees you have. And when you have a single tree, then you are basically back to decision tree. And what you see on the vertical axis is error. And so every time things are going down, you are showing improvement. And so there are three things that are compared here. And the three things that are compared is basically, I could say, two. When m is equal to p, that's all the predictors are considered in each decision making point, then you have bugging. When m is equal to square root of p, then you have random forest. So think of the golden one is the brown or golden type color is bugging, and the green one is random forest. So compared to bugging, random forest is improving. The other one is somewhere in between. That's when the m is not square root of p, but it is half, and it's not helping. So we can just ignore it. And so when we compare bugging and random forest is doing better, which is what we argued for, and it delivered. The other thing, that major point that you can see here is that random forest or even bugging, compared to what you would have done with just a single tree, however you prune it, is giving you a drastic improvement in terms of error. So it was above 0.5 error when it was just a single tree, but when you use random forest, it was close to 0.2, it sounds like, or it looks like from what you see here. And it looks like the tree, after you got to 100 or so of them in your random forest, didn't help very much. These are things that you could find out by doing cross-validation. But you can see that it's not improving very much, but about 100 was a good number. And you also see that it never hurts to have more of these. That's one interesting characteristic about random forest. You could add more and more trees. You may not gain a whole lot in terms of accuracy, but you will never get hurt. It will not go up again. And that's what this figure is showing you. Okay, we looked at bugging, we looked at random forest, and I hope by now you have a working understanding of why random forests work and why they are improved over bugging. There is another method, the third one for today, that I want to tell you about. And I'm going to go a little bit faster on this one because it has a different nature, but it requires a little bit of parameter tuning, which I will talk about, and therefore maybe not the go-to place for most people. In both bugging and random forest, what you are doing is have trees and averaged out, whether they were all of them or a random portion of with selected predictors taken. Otherwise, they were the same. And so you were averaging. What boosting does is have more trees. We are in the business of having more trees. We are still having more trees, but this time they're not equal and then independent and then averaged out or majority taken. Instead, the trees are grown gradually in a sequential fashion. So one tree is added to another tree, to a third tree, to a fourth tree, but the relationship between them is that they are added in such a way that they contribute in a gradual fashion, in a sequential fashion. That is called boosting. And so let me show you the math version of it, and then we'll see how this one compares with random forest for an example. So the tree that we fit in bagging and random forest was for the entire data set. And there was no iteration, there was no sequential nature to it. They were equal. They were the same things, other than in the case of random forest, having to worry about which predictors you are going to use for splitting decisions. The trees were equal otherwise. These ones, the trees are grown in a gradual fashion where you first fit where you gradually fit things that are to the residual. Residual is what the difference is between what you predicted and what you currently are at. And so initially the predictor, the residual will be just the observation, and now you're going to grow B trees. And each time what you add is to the previous tree you have um, a, a, a model that's fitted to the residual, and that's what this F bar B has on it. But you are adding it with a depressed value, a shrunk value, and that shrinking parameter is called lambda. So I had a tree, and I'm adding something to it, but a shrunken version of it, and that's called lambda. And then we keep on doing this. We keep on doing this by looking at the residual, by updating the residual and fitting a new model. By the time we finish, then we add them up. We have these gradually built trees, and these are not equal. We're not going to average them. We add them up because they were done on residuals one at a time. And this method is called boosting. The reason that you see there is a parameter tuning is because we have a bunch of them. There is actually 3 of them, and I'll show that in the next slide. But one of them is this shrinking parameter that you are adding that's called lambda. So this is the idea behind. The idea behind is to gradually learn by having a tree that you will add to the previous one, to the one that you had before, by looking at residuals each time. When you do what I just told you about adding them, and the way the math was displayed was for regression. And for classification, the same way, you do something similar, but this time it gets a little bit messier. And so this book that I mentioned last time has got another version of a book that has got more math details. And so this is where, for those of you who are interested, I wanted to point out where you may find something like that. But there is a package in R called gradient boosted models, which I hope we will find a little bit of time towards later on today to see where this method is implemented. So boosting works for regression as well as for classification. It's not so easy to see what boosting for classification would do, but here is a place to read, and the R package that does something like this is called gradient boost models. And so let me show you the gene expression data I showed you earlier and what boosting does on it. Remember what it was doing. So we've got this 4,700 gene expressions, and out of them we selected 500, and we saw random forest gave us better than what bagging would do. What about boosting? Here is the place where you see random forest and boostings compared. So random forest is green, and we are looking at classification error, so lower is better. And so the boosting is actually doing better when one of them is at one depth and the other one is at another depth. The improvement, you may argue, may not be big compared to probably what you need to get there, but it gave an improvement for this particular data set. And so this is the detailed word explanations for what the figure was showing. Let me show you the parameters to be tuned. One of them we already met. Let me actually have all of them. One of them we already met. That was the shrinking parameter lambda. How much of the tree that we just grew on the residual should be added. And usually this parameter is small, 0.01 or 0.001. That's the kind of values you would use. That was the second one. The number of trees itself, B, how many you would use. The figure that we saw now showed, just like random forest as a function of trees was shown, and we saw, we didn't see a whole lot of improvement when we added more and more trees, and it kind of stabilizes. The same thing is true for boosting. So the number of trees is another tuning parameter. There is a third tuning parameter, and that has to do with how many splits you would do in each tree. And then it's also called the depth, and that's called D. So we've got 3. how many trees we're growing, the shrinking parameter, and the number of splits we are doing in each tree. When you work with d equals to 1, which is one of the results the previous figure showed you, you are looking each of the predictors separately. That's how you can interpret them. When you make it 2, now you're looking at interaction between two variables. And when we make it 3, you are making more of them. That is what the interaction depths of a boosting method would do. So when you have successfully done this, and when we get to the point where you will learn about deep learning, for example, you would encounter, this is one of the places where things get a little messy, because you have many parameters typically, and you don't have any other way than to tune these parameters for your data set, and sometimes that could take time. And so for this particular method, boosting, we have these 3 parameters, and you can fix one and then try others, and usually you've got some intuition for when to change which one and what to work with, but generally there is no prescription for what to do other than to actually tune and find out them. And so I could give you some guidance, or somebody can give you some general guidance. Lambda, you don't start with 0.9 or 0.8. You use numbers like this, 0.01, 0.001. For the interaction depths, you would use 1, see how it works, and you would use 2. And typically people would go with powers of 2, because you are talking about a tree and it is depths. So 1, that's also called a stump, by the way. And then d equals to 2, 4, 8. I don't think there is any problem that I have seen where people would go more than that. So 1, 2, 4, 8. That will be the kind of values that you would explore for D. For the number of 300 is not unusual. We've seen an example where we were looking at up to 400 or 500. Okay. I'm going to get to the code part, but I have to tell you this one so that we can wrap up this. And this is much like what we have seen. You've probably picked up a pattern. Every time we discuss one big topic, there is another one that comes along and is important in a broader sense. This is one of the things you would do when you have supervised learning methods and you've got many variables, typically many predictors, and you want to know what their importance is. This will be part of the thing you would report about your methods. And especially when you have cascades of methods or ensembles of methods that you would use, the importance of variables becomes an important issue. It's not just about understanding the problem and for working with it further, but also if you were to kind of think of a sandwich. If you have your favorite sandwich, you put one layer, and then on top of it you put another layer, on the top of it you put another layer. If you were to have methods that are ensembles and you are many methods are involved in it, then it will help to know the importance of variables in, for example, in a random forest decision. So you have software tools that would give you importance of variables plots like this, and usually they are normalized. And so the way it works for random forest and bugging, for regression or classification in R or other packages, is to see in a random forest, for example, to see what does the variable's contribution in each decision point in the tree be. How much of a reduction, for example, if it was a regression problem, how much of a reduction in residual sum of squares did it result in? And so you could do this and then have it aggregated, and finally you would get a value that you can associate with that variable. So if you were to do this for this heart data set, you will find, and this heart data set is the one that was to help classify people have heart disease or not, and there were 13 of them, I told you. And so these are what you see, these variables are chemicals, so it's thiam, calcium, and they go on like this. This Thi was the one that helped reduce this the most, and so it gets a value 100, and the others would become smaller and smaller. And this is something that you can plot by asking for it in a package. All right, I know I've gone on a few of the slides a little faster, but basically what I wanted to accomplish for decision-based, tree-based methods is now finished. And we looked at decision trees and we liked them because they are interpretable. We disliked them because they don't give us the best prediction. And then we used a bunch of them to make predictions better. And one of the way to make a bunch of them is bugging. And we improved on it, or people who came up with it first improved on bugging by looking at random forest. And there is something called boosting that is can potentially give better results than random forest, but it's got tweaking parameters that you have to work with. But random forest usually does a good job for most of the time, and probably would be, out of these three methods, the one that to recommend safely without having to worry too much to tune parameters. This concludes what I wanted to do. Let me stop sharing for a second. And I'm going to go try to get to the R code part, but let me see if you still are with me. We've got 10 minutes, so you should be ready. Both these slides without the soccer goal and the code that I will be going through now are posted on Blackboard. So I didn't ask Chris to take us there, but he would go there. Does anybody else got a quick question for me before I start showing you some R code? And I'm going to rely on you to go on your own, but I'm going to just at least highlight a few things. We will probably not have a lot of time to go one by one on everything. Any questions for me? Are you with me?
Will you take some time today or on Wednesday to just give us a brief few minutes on how to what you preparing for the midterm?
Not only this, actually, okay, so let me maybe take that one, that question. Next week is when midterm would be, and 11th is Veterans Day, so 13th is what I am deciding to have it. So Monday will be a good day to have a review. If that, I think that will probably work for everybody. So what we will do for the rest of this week is talk about unsupervised learning, and we will talk about principal components analysis in class 3. And that's what I would like to use the rest of this week for. So Monday next week will be a time when I would devote to reviewing things that will help for preparing for the midterm. Does that sound like a good plan?
Thanks.
So will it be a take-home exam or will it be a in-class exam?
It will be take home.
Okay, thank you.
And that will be on the 13th. Any other questions? Did I go extremely fast today, or were you able to follow me along?
It was extremely fast. My hand hurts, but I think I got everything here.
Yeah, I knew I was fast, and I don't think that was too bad in the sense that I think you can come back to this once, but I realized that. So I don't know what the compromise would be. I have a desire to cover a little, many topics, and so this is an important topic. I don't want to not to have it, but I'm not sure if I would have done a whole lot better if I had more time. So I could slow down a bit now, but we still have some time. So let me go to the code part, okay? And you can still ask me questions if you have. If I can locate my R. Okay, let me see here. Come here. Share. Yes. Okay. Do you see my? Brit, can you give me a hands up if you see my screen with R? Yes, okay. So what I will do is try to make this one something that you, when you look at it yourself, you would be able to follow along. We will do two things. One is to see how trees would work. We know their deficiency towards the end, and so ultimately we would make sure that we see how random forest works, for example. But this tree is important because we also would get a chance to see how R does it, and especially when things that are about having to get the tree out, annotate it, and see the things that we theoretically saw them. And so the package in R for doing this is called tree. And so we will install it. That will require it. Library is another way we do. And we are going to use with it a few data sets that are taken from this book. And so that's what you see in the first 3 lines. And we are going to begin by having to look at a data set called car seats. We have encountered this one before. So that's what's happening in the first ones. And in this cars data set, we are going to be looking at cells. And this is the one that has got a lock on the one of the doors and car seat, child seat and things like that. So we are going to look at a variable called cells. and did a histogram on it, and you can see this is what it looks like. This is the raw data set, and we are going to turn this one into a classification problem. And so everything, if the sales was more than 8, we will call it a high. If it is less than 8, we will call it low. So high, yes or no, is how we will turn it. And so this is also another place where you could see how in R you could use the if else command to create a new variable like this. Okay, so we've got a variable called high, and we're going to add this to our original data set. And data frame is a command that you could use, and R now will figure out that this you're working with the original data set, and you're adding a new variable called high to it. That's what has happened in line 11. Now we will begin to work with trees. And I'm going to call the library is called tree, and the function to call it to build the decision tree is also called tree. And what are we going to predict, or going to, like what we have in a regression model, the response? The response is this classification that we will call high, and we are going to use everything except for cells, because that one was the one we turned it into binary, and so we will remove it. And the way to remove a variable from R is by having the minus sign. Otherwise, we are going to work with this car data set. So we build a tree. And so let's get to see what this tree looks like. And so we can write a summary on it, just like we can do on almost any variable, and we get some information about the tree, including, for example, the mean deviance, because this is a binary classification problem. So the mean deviance becomes a meaningful thing to do. We could also plot the tree, and when we plot the tree, it looks like what you see here. And I don't know why it didn't show the rest of it. It should have shown us more bushes and things like that around it. It didn't. So I should probably find out. Maybe when you run it on your code, probably it would behave in a slightly different way. But we have the tree drawn. We could do that. And then we are going to be doing prediction on it. And to do prediction on it, we are going to take a sample. We are going to divide the data set. I think it has got 400 in it, to divide half of it for training and the other half for testing. And because you want to sample, you usually would do set seed. This is where your random number generator would be reproducible. That's what is happening in line 17. And so we have, we're going to take a sample 200 out of the however many rows there are. I think it has got 400 is what it has. In line 18, we are just taking a sample out of the training, and it is of size 200. That's what the sample function in R would do for you. Now we're going to test, and we are going to use everything that's not used for training for test, and that's what the minus symbol in line 19 would help us get. We call this one now in a variable called carseats.test, and we are going to similarly have a variable called high test that is not on the training. And this time now we are going to start predicting. So what you see in line 21 takes the tree, it takes the cells, and we are going to first fit it on the training model. And then we are going to, that's what has happened in line 21. In line 22, we are going to be predicting. The functions in R, the calls we make, are similar. We did something like this when we were doing logistic regression. We did something like this when we were linear models. We have a function called predict that will take as a parameter the fitted model and the data set. And when it is a classification problem, we also want to specify type. Sometimes we are interested in just probability, and sometimes we are interested in the class. In this case, we're interested in the class, whether it is high or low. And so in line 22 now, we have the predict model function called, and we have the fitted model, we have the data set, and we say that we are interested in class. Then we'll start looking at how our prediction is doing. And one of the ways in which you could find out about that is by looking at the confusion metrics, the places where you have correctly predicted and the places where things are wrongly predicted. So that's what table would give us. And here we see we have 200. I'm not sure why I am getting this one exactly right. I think there is something that I have run that kind of make this one not very interesting. If you run it, I'm sure you will get a different value. You should have gotten something that looks like what I wrote in line 20, in line 24, and it should have given us 0.715 as a correct one. There should have been something that is off diagonal that gave a value other than, you know, all 200 of them being correct. I don't have time to go back and redo this now, but I'm going to trust that what you see here is what you get on when you run on your machine, 0.715, which is not a bad number. So we did do a decision tree, and we got an accuracy of 0.715 is what this one would have shown us. Now we could start to do a pruning, and this is what the remaining, you know, lines of code on this one would have done if I had enough time to show you. So what you see here is to use cross-validation to find out where to prune the tree, and so there is a number of, you know, plot parameters that you would get to help you make the pruning size, how far you should go back, identify it this way. And then there is another portion of the code that talks about random forest that I don't have time to do. So you've got the code. Unfortunately, actually, the code that I'm running now didn't give me the number that I was looking for. But when you run it, you will get, if it is necessary, then I would probably complete walking through this code in next time. But I hope you will probably be able to do this yourself, and I will get to start unsupervised learning on Wednesday. Whichever way it is, I have to stop here now and let you go, and I'll see you on Wednesday. So we did not do the second half of our soccer game today complete. We did maybe a portion of it, but let me try to complete this one on Wednesday. I think probably that would be a better thing to do. I don't think there is a big point in rushing this too much. So let me complete this on Wednesday.